This lecture is going to cover Chapter 5, which is stereoisomerism. So we've already looked at different types of isomers. We've encountered constitutional isomers. Constitutional isomers have the same molecular formula, but a different connectivity. They differ in physical properties. So we can compare, this should be methoxymethane and ethanol. So first we have the ether, which is methoxymethane, and then I'll draw ethanol. And you can see both have the same molecular formula, C2H6O, but they differ in boiling point and also other chemical properties. The reason why ethanol is going to have a higher boiling point is because you can have intermolecular H bonds, hydrogen bonds. So it's going to have a higher boiling point compared to the ether. We've already seen different types of stereoisomers when we looked at cis and trans, and we did this with our chairs and our cyclohexanes. Okay. So here I have a cis isomer. The key with cis and trans is that you have to identify substituents on different atoms. And we can also identify cis and trans when we're looking at double bonds. Okay, so I've drawn 3 alkenes here, and I want to identify if the alkenes are cis or trans or don't have a cis and trans relationship. The first alkene is trans. The substituents that are attached to the carbons of the double bond are on opposite sides. The next double bond is cis. The substituents are on the same side of the double bond. The last alkene is not cis or trans because there are ethyl groups coming off of the same carbon. Okay. So again, just to review, cis and trans is a type of stereoisomer, and stereoisomers have the same molecular formula, the same constitution, but they're going to differ in the spatial arrangement of atoms. So we're looking at differences in the 3D arrangement of atoms. Now, much of this chapter deals with mirror images. And so you can think about your hands as being mirror images of each other. Okay? Now, even though they're mirror images of each other, you cannot superimpose your hands. All right? Handedness is very important in organic and biochemistry because of the molecular handedness, or this particular arrangement in space. Okay, this is what makes possible the specific interactions between enzymes and substrates, or drug interactions with receptors. When you have this handedness, you are said to be chiral. And you can think about objects that are chiral. So for example, a ball is not chiral. Okay? A ball is achiral. And when something is achiral, and I'll define it again, it has symmetry. Okay? Whereas these chiral objects do not have symmetry. They are non-superimposable mirror images. Some other examples of chiral objects: the spiral binding of a notebook, or a machine screw with a right-handed thread. Alright, so when we think about molecules, we can think about molecules as objects. And they have definite shapes and geometries. And so organic molecules have a handedness or a chirality. And what we're going to do is we're going to look at this with regard to substitution patterns on sp3 hybridized carbons. So you only have to determine the chirality for sp3 hybridized carbons. When we have a chiral center, it is going to have a particular arrangement of atoms. That arrangement, okay, can exist so that there are two molecules that are not the same as their mirror image, and they are non-superimposable. And this pair will be referred to as an enantiomer. So an enantiomer is a relationship between a pair of molecules. Now, when there is, with an enantiomer, the arrangement has to differ at each chiral center. So, if you have one chiral center, then the configuration is different around that chiral center, and you have a pair of enantiomers. If you have two chiral centers, the arrangement around the two chiral centers will be different, and you will have a pair of enantiomers. So if we look at the atoms that I have below, or the molecules that I have below, here I have a bond line structure of 1 bromo, 1 chloroethane. Here I have a condensed structure. And then what I have drawn down here are your stereoisomers. What I want to point out is that the bond line and the condensed structure do not indicate 3D arrangement of atoms. We use wedges and dashes to indicate stereochemistry. And so, what I've drawn here is that I've differed the arrangement of the methyl and the hydrogen. And as a result, and the bromine, sorry. And as a result, the configuration around that chiral center is different. Don't worry about R and S. We'll talk about that in a little bit. All right. What I want to emphasize is that sometimes it's easier to determine if something is achiral. Okay? And so anything with a plane of symmetry or a reflection of symmetry, or a center of symmetry, is achiral. And so usually an achiral object or an achiral carbon will have two or more of the same substituents. So if you look here at 1 bromo, 1 chloromethane, you can see that the central carbon, I'll just draw it a little bit bigger, has 2 hydrogens attached to it. So this carbon is achiral. And again, I want to emphasize that we're only looking at sp3 carbons. So typically, we'll see 4 different substituents attached to the carbon. So there are different ways that we can draw chiral molecules. Here I've shown 2 different representations, okay, where we have a partially condensed structure, and here we have the bond line representations. In both instances, you are using the wedges and the dashes to indicate stereochemistry. When you are drawing chiral centers, try and keep the carbon framework in the plane of the page, and then put the other atoms or groups of the chiral center toward and away from you. This will help in trying to determine the configuration around the chiral center. When you need to draw the different enantiomers, what you can do is you need to switch 2 of the groups. So here I've shown you 2 examples. We have a methyl and an ethyl coming off of this chiral carbon here. And if we switch these 2 groups, we can make the enantiomer. The other option is, instead of switching the 2 alkyl groups, is that we can switch the configuration of the OH and the hydrogen. So here, when we switch the OH and the hydrogen, the OH is now going into the page and the hydrogen is coming out of the page. And so now when we're looking for chiral centers, we're looking for the first point of difference. Okay? So it's easy to identify our chiral center. Well, it's not easy, but chiral centers that are in open chains are a little bit easier to identify than when you're looking for a chiral center in the ring. So if we look here at these ring examples that I have, you can see that I've highlighted the chiral centers in red. And so to explain the point of difference, okay, we'll start with this chiral center up here. This carbon has a hydrogen attached to it. It has a methyl group. Right. And then when we look at the next carbon out, both of those carbons are CH2 carbons. So we have to go to the next carbon, which I'll highlight in red, and you can see that this carbon here is a CH2, whereas this carbon is a CH with an OH. So here is your first point of difference. So that this is a chiral center. Okay. So now what we need to do is just figure out how to assign the configuration of a chiral center. So if you've looked through my notes, and if you remember from last week's class, we designated the chiral centers R and S, and we used priority rules based upon the Kahn-Ingold priority rules to rank our substituents. So what we're going to do is we are going to first rank the substituents. If they are from highest to lowest, and it's clockwise, then we have an R configuration. If it's highest to lowest and it's counterclockwise, then we have an S configuration. And this is based on the Latin for right and left. If we look at the priority rules, the first rule is what we do is we look at the 4 atoms directly attached to the chiral center, and we're going to rank them according to atomic number. The higher the atomic number, the higher the priority. H is typically the lowest priority. It's always the lowest priority if there's a hydrogen. And then the priority increases as you increase in atomic number. If we cannot assign priority based upon ranking the first atoms that are attached to the chiral carbon, then we have to look at the second, third, and fourth atoms until we can find the first point of difference. Here, if we look at this carbon, it has 3 hydrogens attached to it. Okay. Then what we can do is, if we had an alkyl substituent, we would say it would be higher priority because it's carbon with 2 hydrogens and a methyl group, and so forth and so on. And so what you're going to do is you're going to rank the point of difference based on atomic number. The next thing that we need to look at is how to deal with double bonds. And so what we need to do is that we need to have apples to apples. And in doing so, what we'll do is we'll separate a double bond out so that you have the 2 carbons attached to each other, but then you, I don't want to say pretend, but then what you do is you attach a carbon to each of those carbons because it's a carbon-carbon double bond. You'll treat a carbonyl as a carbon bonded to 2 oxygens, okay, and an oxygen bonded to 2 carbons. A triple bond, okay, what you do is you have your 2 carbons that are bonded together, and then you're going to just separate the pi bond. For each pi bond, you add a carbon. Okay, so here we have 2 pi bonds, carbon, 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 carbon. In order to assign R and S configuration, you want to orient the group with the lowest priority pointing away from you. You're going to orient this like a steering wheel. So that the axle of the steering wheel is pointing away from you. And then what you're going to do is you're going to look at the other three groups, and they're going to radiate out like the spokes of a steering wheel. You're going to read the three groups in order from highest priority to lowest priority. Again, if the groups read in a clockwise direction, you have an R configuration. If the groups are counterclockwise, it's S. And so here are a couple of examples where I have the configurations of the chiral carbons already drawn in. And you can see, if we rank substituents, the hydrogen is lowest priority, the chlorine is the highest priority. Now we have two alkyl groups here. This alkyl group is a CH3, okay, and here we have a CH2 attached to another C, so that the ethyl would be higher priority, so it would be 2, the methyl would be 3. Counterclockwise, we have an S orientation. I highly recommend the use of models. Okay, here what we can do is don't worry about Z for now, we'll learn that later on. We're just looking at chiral centers. So that's just R and S. So again, let's rank the groups. The hydrogen is the lowest, the chlorine is the highest. We go to the next atom out. We have CH2 on one, and on the other one, it's a double bond, so we need to separate out the double bond. Okay, here is the bond between the two carbons. There's also a hydrogen on that carbon. Because we have one pi bond, we add one carbon to each carbon of the double bond. And we can see here we have a carbon with two hydrogens and another carbon, whereas this carbon is attached to two carbons and one hydrogen. So this carbon here would be assigned a 2. And then we would assign that carbon a 3. The book does something interesting, which I like. What we can do is redraw everything. And instead of drawing in the actual atoms, let's just draw in the groups by priority. So it would be 1, 4, 2, 3. The lowest priority group is pointing away from us. We're going clockwise. The configuration is R. Alright, so this is how you go through and you rank priority and then assign the configuration. So when we talk about a chiral center, we're referring to a carbon with 4 different groups attached to it. A stereocenter is also used to describe a carbon bonded to 4 different groups, but the definition is much broader. A stereocenter is an atom about which the exchange of 2 groups produces a stereoisomer. When we have stereoisomers, they can be chiral and achiral. Achiral stereoisomers cannot exist as enantiomers, but they can exist as diastereomers. Formally, diastereomers are stereoisomers that are not mirror images of one another. They can be chiral or achiral objects. Enantiomers must be chiral. So diastereomers have a different 3D arrangement of atoms. However, they do not have to be chiral. They can be chiral and they can be achiral. So if we look at this example below, I have a pair of enantiomers for erythros and a pair of enantiomers for threose. What we can see is that here the configuration for the enantiomers of erythros is RR and SS. So for the pair of enantiomers, the configuration differs at each chiral center. There are also 2 chiral centers in threose, And you can see one is R and one is S and one is S and one is R. Now let's just put A, B, C, and D here. And so A and B are enantiomers and C and D are enantiomers. A and C are diastereomers. B and C are diastereomers. And then A and D are diastereomers, and B and D are diastereomers. Just to generalize, when you have a molecule with n chiral centers, there can be a maximum of 2 to the n stereoisomers. This is a maximum. It's not an absolute number. When you have at least 2 chiral centers, you can have diastereomers. Now, again, I just want to emphasize the difference between enantiomers and diastereomers. Enantiomers have opposite configurations at all chiral centers. Diastereomers have opposite configurations at some chiral centers. Diastereomers have different physical and chemical properties. Enantiomers will have the same physical and chemical properties in an achiral environment. Water is an example of an achiral environment, but they will have different chemical properties in a chiral environment. The pocket of an enzyme is an example of a chiral environment. Okay. Any compound that has a single chiral center must be chiral. This is not the case when we have 2 chiral centers. So if we take this example here where we have cis and trans dimethylcyclohexane. So the first molecule is cis. The second trans. Here you can see. All right, well, let's address this first. We have 2 chiral centers here. However, what you can do is you can fold the molecule in half and you have a plane of symmetry. So this molecule is achiral. We do have chiral centers, but the molecule itself is achiral. Here, when we look at the trans isomer, again, we have 2 chiral centers. But there is no symmetry here. So, this molecule is chiral. Okay. Any compound that possesses a plane of symmetry in any conformation is achiral. And so any kind of reflectional symmetry is going to render a molecule achiral. So if we look at tartaric acid, well, we can see here's the bond line structure for tartaric acid. You can see that we have 2 carboxylic acids and 2 OH groups. When we use the Fischer projections, and I'm sorry I didn't explain this because I have recall as far as that we did Fischer projections in class. For those of you who weren't in class or just need a review, with a Fischer projection, okay, the way a Fischer projection is represented is that the vertical, no, let's do this again. Okay, so here's a Fisher projection. And what this means, and I'm sorry I didn't re-clarify this. The ends are going into the page, and the horizontal lines are coming out of the page. Okay? Alright, so let's go back up and look at tartaric acid. Alright, so with tartaric acid, you can see that we have a pair of enantiomers where we have an RR and an SS. Now, if we just change the configuration at one of the carbons, so we change the second stereocenter to an S, where we just flip the configuration of the OH and the H, okay, and then we draw the enantiomer where we change the configuration at both chiral centers, we have RS and SR. You can see that there is a plane of symmetry here. In addition, when you have the configuration inversed and have the same groups attached, the same substituents, you have a meso compound, or you have symmetry. Okay? And so a meso compound means we have the same compound. These two molecules are the same molecule. They are achiral but contain chiral centers. There is a plane of symmetry. When we're trying to determine if a molecule is chiral or not, we can look at its optical activity. So light consists of waves that oscillate in an infinite number of directions. If we pass this beam of light through a polarizer, the light waves in a single plane pass through and the light can be plane polarized. Now, when we have a chiral molecule, what it will do is it will rotate plane polarized light. So chiral molecules rotate plane polarized light. Okay? The angle at which the light is rotated is called alpha. Now, alpha is a physical property. It's defined for a given temp and wavelength of light. Okay. Enantiomers are going to rotate plane polarized light, but in opposite directions. Meso compounds do not rotate plane polarized light. You can designate the rotation using positive and minus. When you rotate, I'll push the screen back up so that the writing isn't as jumbled. When you rotate plane polarized light to the left or counterclockwise, your Lavora rotary, and it's minus. When you rotate light to the right, it's clockwise. The solution is dextrorotary. This has no correlation to R and S. The other thing, a couple other points. A racemic mixture, which is a mixture of two enantiomers, a 50-50 mixture. Okay, so a 50-50 mixture is a racemic mixture. It is not optically active. When you have an excess of one enantiomer, you can still rotate light, but the angle, or alpha, will be different from the alpha of the pure enantiomer. We can use this difference to calculate the enantiomeric excess. In order to calculate the enantiomeric excess, or the percent excess, the percent enantiomeric excess, what you're going to do is you're going to use the alpha observed over the alpha of the pure, and you times that by 100. You will be responsible for doing problems of this nature. One more side note, and just this might help clarify with the homework. So in the homework, I gave you a Newman projection. Okay. When you draw Newman projections, they are stereoisomers. Okay, so here I have the OH groups and they're gouged to each other, and here I have the OH groups and they are anti to each other. So these are two stereoisomers. However, because rotation around a C bond is so rapid, they are not isolatable. So you can't isolate one isomer from another. The other thing that you need to realize is that there's no stereochemistry here. I'm just indicating where the groups are in relation to each other. I'm not giving you the absolute configuration at the carbon. Okay. So while they are stereoisomers, you cannot determine if there's chirality here, because I'm not giving you any kind of three-dimensional arrangement in space. We can rotate freely around the axis, around the C2, C3 axis. And so you can generate different arrangements in space, but you cannot say if there are chiral centers or if anything is well, you can say if it's a chiral center because it'll have 4 different groups, but you cannot tell me what the absolute configuration is at the carbon or draw an enantiomer based upon a Newman projection. I will say that in order to convert, so between these two types of butanol, they're both 2-butanol, you need to break a carbon OH bond. Whereas when you're converting between different conformations of Newman projections, you're just rotating. You're not breaking any bonds. So this is an important distinction to make. Okay, stereoisomers have a different arrangement in space. So Newman projections are stereoisomers. You can determine if a carbon is chiral because you can see if it has 4 different groups attached to it. However, you cannot determine the absolute configuration of a carbon from a Newman projection. You need to have wedges and dashes. I hope this clarifies some of the questions that arose from Thursday's lecture. If you have any more questions, please feel free to contact me.